Hello. In this lecture, we are going to continue with the topic that we were discussing in the previous lecture. That is, we are going to continue with Cauchy sequences today, and then we lead to something called as series. Okay. So most of the things I hope you've done in real analysis class. So in this lecture, I'm going to really briefly go through all the concepts that you have already studied in real analysis. So sequence and series in C. This is the second lecture. The first lecture was a brief lecture on what do we mean by sequences, what do we mean by the conversions of the sequences, so on and so forth. Today we are going to continue with something called as Cauchy sequences. I hope you might have studied Cauchy sequences in real analysis. Almost similar definition, almost like it is similar here as well. So let us, without wasting time, let us start with Cauchy sequences today. So one of the ways of characterizing whether a sequence is convergent or not, we we take we usually consider the definition of the Cauchy sequences, and this is something that we do in real analysis also, and this is what we do even in the complex analysis also. Um, so a sequence Zn, right here, a sequence Zn is said to be Cauchy if Zn minus Zm modulus, if for a given epsilon, for any given epsilon greater than 0, there exists some n naught or n belongs to natural such that for all m and n greater than equals to n belongs to natural, Zm minus Zn modulus is less than epsilon. So this is the similar definition. So Cauchy sequence is a sequence where, see, what does it mean? It means that, so if I'm saying that the elements of the sequence are convergent, if I say that the sequence is convergent, let's say to Z, then there would be some natural number after which the elements of the sequence will also start will also start becoming closer and closer. So this is how what is meant by Cauchy sequence. So a sequence Zn is said to be Cauchy if for any given epsilon greater than 0, there exists some n belongs to natural such that for all m and n greater than equal to capital N, Zn minus Zn will be less than epsilon. So this is called as Cauchy. And in fact, much bolder statement in R also was there. And because after all, you see Z, whether you consider Z or you consider R square, this is one and the same thing. And yesterday also I told you, if Zn converges to Z, then imaginary part Zn and real part of Zn must also be convergent. So a sequence Zn converges to Z if and only if imaginary part Zn and real part Zn converges. So basically it is equivalent to the convergence of sort of R only. So the statement here also remains the same. A sequence Zn is Cauchy if and only if it is convergent. So it implies that if you prove that a sequence is Cauchy, then it is convergent. And if a sequence is convergent, then it is obviously Cauchy. This is what is, I'm not going into the proof of all these things. This is something that you already know. Another theorem that you might have studied in your real analysis was Bolzano-Weierstrass theorem. You know that from your real analysis also that every sequence has a monotone subsequence, and if the sequence is bounded, then that monotone subsequence which I've told that it is a monotone will be bounded and it will be convergent. So Bolzano-Weierstrass theorem says that every bounded sequence in R has a convergent subsequence. Almost like similar statement you will have in complex analysis. That is, let Zn be a bounded sequence in C, be a bounded then there exists a convergent subsequence. Then there exists a convergent subsequence. So this is an important theorem. You might have already studied it in your real analysis. I'm not going to elaborate much on it, but a little bit of understanding will help. So let me just elaborate a little bit, not completely proof, but a sketch of proof. So you already know that if Zn is a sequence, then let me write that real part of Zn be described by some xn sequence and yn be equals to imaginary part of Zn. If Zn is bounded, if Zn is bounded, both real as well as the imaginary part are bounded. It implies what? It implies that xn and yn are also bounded sequences in R. Are bounded subsequences, bounded sequences in R. Now, already from Bolzano-Weierstrass theorem for real sequences, Bolzano-Weierstrass theorem for real sequences, you already know something that is uh, there exists some convergent subsequence. There exists some convergent subsequence. So from that, we already know that there exists a convergent subsequence. So let's say for xn, we have some x and k, which is convergent. And similarly for yn, there would be some y and k, which is convergent. Okay, and some, let's say, some different, I'll say this y and k are, this also converges to y. So therefore, this is convergent. And let's say this converges towards x. So what does it imply? It implies that there exists some convergent subsequence z and k converging to what? Converging to x plus iota y. If x and k is a convergent subsequence converging to x, y and k are is a convergent subsequence converging to y, then obviously there would be some uh, uh, z and k are, let's say, which converges towards x plus iota y. It implies what? It implies that Zn has a convergent subsequence. Okay. So it is a similar statement that you might have seen in real analysis also. In complex analysis also, uh, the Bolzano-Weierstrass theorem suggests the same thing. That is, if Zn be a bounded sequence in C, then there exists a convergent subsequence in Zn. Okay, so there exists some convergent subsequence in Zn. I think this is quite clear. Okay, a little bit more about it. Just not giving you proof. Let Zn be, I think this you have to do on your own, proof on your own. I'm just giving you a sort of theorem, a statement. Let Zn be a bounded but non-convergent, bounded but non-convergent sequence in C. Then there exist two subsequences. Then there exist two subsequences converging to different limits. Converging to different limits. So this is some very important theorem. See, let's say I give you one example to illustrate this. Let me give you an example to illustrate this. Let us say Zn. is equals to minus 1 raised to power n plus iota n upon n plus 1 for all n belongs to natural. So let us say this is Zn. Now you see, if you just think about the even subsequence z to n, it will be equals to 1 plus iota 2n upon 2n plus 1. And which certainly will tend towards 1 plus iota. Also see z2n plus 1, what it is equal to. It will be equals to minus 1 plus iota 2n plus 1 divided by 2n plus 3. And certainly it will tend towards minus 1 plus iota. So one can clearly understand that Zn is not convergent. Zn is not convergent. And however it is bounded, however it is bounded. So if it is not convergent and bounded, then there exist two subsequences. Then there exist two convergent subsequences with different limits. So this is one of the example from which I have illustrated the same concept. I hope it is clear. Okay, another important point is, let's see, what is a limit point of a sequence? If I'm saying that z naught is a limit point of sequence, then in the neighborhood of z naught, you can find infinite members of the sequence except z naught. So let's say if I'm saying that if I'm saying let's say zn is equal to minus 1 raised to power n. Now any neighborhood of 1 will contain infinite members of the sequence. So for example, if I say what is z1, z1 is minus 1. What is z2? Z2 is 1. What is z3? Z3 is minus 1. So on and so forth. So if I make any neighborhood of minus 1, there are infinite many members of the sequence, because you know that z3 is also minus 1, then z5 is also minus 1, z6 is also z7 is also minus 1, z1 is also minus 1. So clearly minus 1 and 1 are two limit points of the sequence. Now one important thing I'm writing here, most often people get confused. Always remember one thing, that if Zn converges towards L, then L is limit also. L is limit also, and it is limit point also. So limit L is also the limit point of the sequence. It is by definition itself, because you know that if Zn converges to L, it means Zn minus L mod is less than epsilon for all n greater than equal to capital N belongs to natural. So Zn, the neighborhood of L, contains infinitely many members of the sequence Zn. So clearly L is limit as well as the limit point of the sequence. However, converse is not true. Converse is not true. What do I mean by that converse is not true? I mean that it may be possible that sequence may have limit points, but it is not, they are not limit. May have limit points, but they are not limits. Example I have already given you. So if I take this example again, that is Zn is equal to minus 1 raised to power n plus iota n upon n plus 1. Clearly, Zn converges towards minus 1 plus iota. Sorry, Z2n plus 1 converges toward, and Z2n converges towards what? 1 plus iota. Both of them are limit points. But Zn, the sequence, neither it converges towards minus 1 plus iota, nor it converges towards 1 plus iota. So clearly, I can say that the sequence does not have a limit. So both of these points are limit points, but they are not the limit of the sequence. I hope it is clear. Okay, so I hope you are aware of limit now. So basically, again, let me just give you, if you've forgotten it, then just think about it. I have given you two things. If Zn is convergence sequence and it converges towards, let's say, Z, then real part of Zn converges towards a real part of Z, and imaginary part of Zn converges towards imaginary part of Z. And this was, I think, I proved that this is if and only if statement. Similarly, another important thing is if Zn converges to limit L, then Zn minus L mod can be made less than epsilon for all n greater than equals to n naught belongs to natural. I hope both of these things you know. I just used both these things here. Okay. Now, just giving you, if you've forgotten it, see, this is what I was trying to explain, limit points and limit. Now, if you've forgotten it, just think, I gave you an example. I think just memorizing for just revisiting the concept. So 1 upon n plus iota n minus 1 divided by n. What do you think this sequence? So clearly, this sequence converges, it you can see that xn converges, xn what is what? Xn is 1 upon n. And what is yn? Yn is simply n minus 1 upon n. So this converges towards 0, this converges towards 1. So it is quite evident. It is quite evident that Zn would converge towards iota. Let us see if it is not the case. So if Zn converges towards iota, it implies what? Zn minus iota mod. Let us estimate this. It is equals to what? It is equals to uh, Zn minus iota would be 1 upon n plus iota 1 minus 1 upon n and minus iota modulus. So it would be simply 1 upon n plus, sorry, minus iota upon n modulus. And which certainly is equal to modulus of 1 minus iota divided by n. So z minus iota is this, and certainly this will be equal to what? It will be equal to root 2 upon n. You know that modulus of 1 minus iota would be root. It will tend towards 0. So clearly, or in other words, you know that as n tends to infinity, you know that root over 2 upon n converges towards 0. That implies that root over 2 upon n minus 0 difference can be made less than epsilon for all n greater than equal to n naught belongs to some natural number. So basically it implies that Zn minus iota can be made, modulus can be made less than epsilon for all n greater than equals to n naught belongs to natural. So clearly the limit Zn would be equals to iota. So I have proven it both ways. I hope you must have remembered this particular question I've already given you in the previous lectures. So all these things you have already studied in your real analysis also. So therefore, I'm not much stressing on it. So next is, okay, so I hope this is quite clear. Now, okay, so last thing that I wanted to discuss was, discuss means I'm going to write a result. As I told you that all these things you have already studied at your real analysis classes. So I will not stress much here. So now let Zn be a bounded sequence in C. Now, if there exist Z belongs to C such that every convergent, every convergent subsequence Zn has the same limit Z as the same limit as that Z, it implies what? It implies that limit Zn is equal to what? Z. So if every convergent subsequence of Zn converges to the same limit Z, then the limit of the sequence is also the same, that is Z. I hope it is clear. Okay. So this is all most of the things that usually sequences in C I would have wanted to discuss. Another small concept is null sequences. Not important as such, but definition wise, you think about it. What is a null sequence? So a convergent sequence with a zero limit is called as the null sequence. So basically, if Zn converges towards Z naught, then if I want to make a sequence which is Zn minus Z naught, clearly this will converge towards zero. So therefore, this is a null sequence. So this is a null sequence. Okay, so it gives you another way of writing things. That is, if you are considering any convergence sequence, let's say Zn, then it can be written as what? It can be written as Z naught plus Zn minus Z naught clearly. So what you can do, you can write that every convergence sequence can be written as the sum of some fixed number and a null sequence. So you can write any convergence sequence as a sum of fixed number and a null sequence. Okay, one of the simple example of null sequences Zn. So this sequence will converge towards zero if modulus of Z is less than 1. So clearly this is a null sequence. Okay, so for this we need to prove that let epsilon be given. Let epsilon greater than 0 be given. Now we have to find some value of n such that Zn minus 0 modulus should be less than epsilon. Okay, for all n greater than equal to capital N. So if at all I am able to, if I'm able to find this particular capital N, if I'm able to find this particular capital N, then this particular capital N such that Zn minus 0 mod can be made less than epsilon for all n greater than capital N, then I would say that limit Zn is equal to what? 0. Now see, already we know that if I want to find Zn minus 0 modulus, if I have to estimate it, it implies that it will be equals to this modulus, and this will be equals to modulus of Z whole power n. If it is less than epsilon, I have to find this capital N. Let us just assume that that epsilon be given to us. So let it be the scenario. Then modulus of Z raised to power n less than epsilon. Take log both sides. It implies log mod Z is less than log epsilon. And you know that already, since modulus of Z is less than 1, you know that log mod Z would be simply a negative number. It's a negative number. Since it is negative, so I know if I divide it, so this inequality would change. So this is log epsilon divided by log modulus Z. Since we want to find since we want to find what? Since we want to find an integer. So what I'll do, I'll simply take n greater than n, where n is equal to what? I'll just take a, what you can say, greatest integer to it and just add 1, so that I'm skipping to the next integer. So if n is greater than n, so greater than n, where n is what? Log epsilon divided by log modulus Z plus 1. Then it implies what? Then it implies that Zn modulus or Zn minus 0 modulus is less than epsilon. So I can write that given epsilon greater than 0, Zn minus 0 mod can be made less than epsilon for all n greater than capital N belongs to natural, where capital N is what? It is equals to log epsilon divided by log modulus of Z plus 1. So it implies what? It implies that limit Zn is equal to 0. So clearly this Z raised to power n is a null sequence. Okay. Had it been the case Zn with mod Z greater than 1, then that is a divergent sequence. Then it is a divergent sequence. And what about the elements which lie on the unit circle? What about them? Here nothing can be said. Why nothing can be said? Let us say if I'm taking units elements on the unit circle. Let's say if I take 0 comma iota. So now Zn is equal to what? Zn is equal to iota raised to power n. This is not convergent. If I take Zn is equal to 1, this also lies on unit circle, then it is convergent. So you cannot say anything with certainty on the points lying on the unit circle. But certainly you can say that if mod Z is greater than 1, then the sequence will be divergent. If mod Z is less than 1, sequence Z raised to power n is convergent, and rather it is a null sequence. So I hope all these things you might have got. We are going to start with series in this next lecture. Till then, take care. Bye-bye.